Let's build a machine learning model together. For this project, we'll be building a neural network in Python to predict potential credit card fraud from real-world data. And this is something honestly anyone can learn to do, so let's get into it. First, I'm looking for a dataset and I settled on this one from Kaggle. This is real-world transaction data, so before touching any code, I always make sure to get a good look at it. There are so many feature columns in this dataset, so let's break it down. The time column specifies how many seconds have passed since the very first transaction, the amount column specifies the transaction value, and the class column labels whether the transaction was fraudulent or not. The first thing I'm noticing is class distribution. Almost every single transaction in the dataset is labeled with a 0, meaning it's not fraudulent, and fraudulent transactions are extremely rare. This information will really come in handy later on when we're evaluating the model, so we can make sure we're not being overconfident. We also definitely need to take a look at some of the dynamics of our dataset. All of the feature columns in the middle here have already been anonymized and PCA transformed, so they're in a range that's very close to 0. However, it's important to see that the time and amount columns here are not on the same scale, and their magnitudes differ sharply from the rest of the columns. These are all things we'll keep in mind for when we get to the Python very shortly. And now that we know our data, we can actually get coding. And just like with every other machine learning problem, I'm starting by importing all of the necessary dependencies. We have NumPy for math, Pandas for data, a bunch of tools from scikit-learn for our machine learning toolbox, and we're also importing Keras from TensorFlow to run our neural network. And now it's time to load in the dataset and make sure everything looks as expected. Now I'm splitting the dataset into X and Y, where X holds all of the feature columns the model is allowed to learn from, and Y is the label itself, which tells us if the transaction was fraudulent. So the model is going to try to predict Y using X. Now that that's out of the way, let's think back to some of the data exploration we did. While most of the feature columns were already scaled, time and amount certainly were not. So we're scaling both of these columns to match the units of the rest of the columns so the model can learn from them fairly. Only after all of these transformations are done, it's time to split the data. We're leaving 80% for the training data, which the model is allowed to learn from and find patterns in, and the other 20% goes to the testing data. And we'll use this later on to evaluate the model's performance on unseen data. Okay, now we can actually design the neural network, and if you've never heard of a neural network before, think of it like this. It's a system that takes a bunch of input numbers, mixes them together using adjustable knobs called weights, and then learns how to turn those numbers into a final prediction by tuning those knobs over time. So now let's build one of our own. The first question I'm thinking about is, what do I want the network to output? In fraud detection, I don't just want a yes or no, I want a probability. For example, this transaction has a 2% chance of being fraud, or this one is 90%. So I designed the output to be a number between 0 and 1. That's why my final layer is a single neuron with a sigmoid activation. Sigmoid is just a function that squishes any number into the range from 0 to 1, so the output naturally behaves like a probability. Now we work backwards. How do we get to that output? The network needs layers in the middle that can learn patterns. So I use a couple hidden layers to let the model learn curved, more complex relationships. But I'm keeping it small on purpose. This is tabular data. I mean, there are tens of thousands of rows of transactions. If I make the network huge, it might memorize the training data instead of learning those general rules, especially because fraud is so rare. So my goal isn't to make the network really deep, it's to make it learnable and stable. So I'm choosing a couple dense layers. Dense just means every neuron looks at every input from the previous layer. Now, inside each layer, I have to choose an activation function. This is where people tend to get lost, so here's the simple idea. Without activations, the whole network would basically behave like one linear equation. It wouldn't matter how many layers you stack. It still couldn't learn the complicated shapes and patterns of the data. Activations are what give the network the ability to learn nonlinear patterns. For this model, I'm using ReLU for all of my layers, and it's incredibly simple. Essentially, if the input value is negative, it becomes 0, and if it's positive, it stays the same. So it's like a gate. It either turns a neuron off or lets it pass through. And our last design decision is, how do we stop the model from overfitting? Overfitting is when the model learns the training data too specifically, like memorizing all the answers instead of learning the concept itself. Fraud datasets are especially risky for this because the fraud examples are rare and unusual. A model can accidentally learn weird quirks instead of real signals. So I'm adding dropout. Dropout is like training with distractions. During training, it randomly turns off some neurons so the model can't rely on one specific path. That forces it to learn more general patterns that survive even when parts of the network are missing. This is one of the easiest ways ways to avoid overfitting in a neural network. Next, it's time to finally compile the model, which basically means we're choosing how it learns. There are big three choices here: the loss function, the optimizer, and what metrics we track. The loss function measures how wrong the model is. For a binary prediction problem like fraud versus not fraud, I'm using binary cross entropy, which heavily punishes the model when it's confidently wrong. The optimizer is how the model updates its weights. I'm using Atom because it's reliable and usually works well without tons of tuning. Now let's focus on the metrics, and this is where fraud detection is different from a lot of beginner problems. Accuracy is basically useless here because if the fraud is less than 1% of our dataset, a model can get 99% accuracy by predicting that none of the transactions are fraud. That looks amazing, but obviously does not work well in practice. So instead, I'm tracking precision, recall, and PRAUC, which reflect how the model is doing more accurately. Now we're actually training the model, but we're not just sitting back and relaxing while it runs. We have to deliberately watch the learning curves. If the training metrics improve but the validation metrics don't, that's a sign the model is memorizing specific coincidences and is at risk for overfitting. That's why I'm also using early stopping, which automatically stops training when the model stops improving on validation data. And at the end, the model is ready to output a probability for each transaction. That's the whole point. The network is a risk scoring machine. And here are the top 10 highest risk transactions that the model predicted from this dataset. And that's all for today, but don't forget to save this video for your next machine learning endeavor and follow for more breakdowns. See you in the next one.